Early 1944, Wright Field, Dayton, Ohio. A test pilot steadied his hand on the throttle of the P-51 Mustang as he pushed past the standard war emergency power setting. The Packard Merlin engine roared as boost pressure climbed to 75 inches of mercury, fed by a new experimental fuel designated simply as Grade 150. The airspeed indicator swept past numbers that represented the edge of what Allied fighters had previously achieved. At 25,000 feet, the Mustang was accelerating through 448 km/h, racing toward 490. The test engineers on the ground exchanged glances as the radio crackled with the pilot's report. This was not an incremental improvement. This was a revolution wrapped in purple-dyed aviation gasoline. A chemical advantage so profound that it would render obsolete every assumption the Imperial Japanese Navy and Army Air Forces held about American fighter capabilities. The war in the Pacific was about to change, and the catalyst was not a new aircraft design or a brilliant tactical innovation, but rather a fuel that allowed existing fighters to perform at levels that defied Japanese expectations. What Japanese command did not yet know was that American and British fuel chemists had achieved something Japan's petroleum-starved empire could never match. While Japanese fighters struggled with low-octane fuel averaging 87 to 92 octane, limited by scarce oil reserves and bombed refineries, American production lines were pouring out aviation gasoline with a performance number of 150. The implications were staggering. A P-51 Mustang running on standard 130 grade fuel could reach 437 km/h at 25,000 feet. The same aircraft, flown by the same pilot at the same altitude, running on 150 grade fuel, could exceed 490 mph. Japanese pilots who had built their entire tactical doctrine around maneuverability, the Zero's legendary turn radius, the Oscar's climbing agility, were about to discover that the Americans had fundamentally altered the equation of aerial combat. Before we continue, click that subscribe button, like this video, and let me know in the comments where you're watching from. It brings me great joy knowing that these war stories and lessons get to people all over the world. Your support helps us bring more thrilling war stories, and trust me, you won't want to miss them. Now, let's get back to the story. The Mitsubishi A6M0 had a maximum speed of 350 mph at altitude. The Nakajima Ki 43 Oscar could reach 330 mph under optimal conditions. The newer Kawanishi N1K2J George, Japan's most advanced fighter, topped out at 369 mph. Against Mustangs running 130 grade fuel, Japanese pilots could at least attempt engagement on favorable terms, closing distance, forcing turning battles, exploiting their lighter airframes. Against Mustangs running 150 grade fuel, Japanese fighters were operating at a fundamental speed disadvantage that no amount of pilot skill, no tactical cunning, no doctrinal adjustment could overcome. The Americans could dictate every engagement. They could choose to fight or refuse combat at will. They had become untouchable. Japanese aviation doctrine had been forged in the skies over China, refined through countless engagements where agility determined survival. The Mitsubishi A6M0, introduced in 1940, embodied this philosophy perfectly. Stripped of armor, built with lightweight aluminum alloys and powered by the Nakajima Sakai engine, producing 1,130 horsepower, the Zero could outturn virtually any fighter in the world. Its roll rate was exceptional. Its climb performance at low altitude was remarkable. In the early war years, Allied pilots who attempted to dogfight Zeros on their terms died quickly. But this design philosophy came with constraints Japanese engineers understood but could not overcome. Maneuverability required light weight. Lightweight meant minimal armor protection, limited fuel capacity for the engine's power output, and crucially, engines that operated at lower compression ratios to avoid catastrophic detonation with the low-octane fuel Japan could produce. Japan's petroleum situation was dire from the war's opening day. The home islands possessed virtually no natural oil reserves. Every gallon of aviation gasoline required imported crude oil from the Dutch East Indies, transported across submarine-infested sea lanes, then refined in facilities that were primitive compared to American installations. Japanese refineries in 1942 could produce approximately 87 to 92 octane fuel in meaningful quantities. Premium fuel approaching 100 octane existed, but only in volumes sufficient for elite units and critical operations. This bottleneck imposed hard limits on engine design. The Nakajima Sakai engine in the Zero, the Nakajima Ha-115 in the Oscar, even the more powerful Mitsubishi Kasei in the Betty Bomber. All were designed to operate on fuel that would have been considered inadequate for frontline American fighters. Higher compression ratios that could generate more horsepower would cause detonation and engine failure with Japanese fuel. Japanese engineers knew this. They designed accordingly. They built engines that prioritized reliability and efficiency over raw power. By mid-1943, Japanese intelligence assessments of American fighter capabilities reflected a dangerous confidence. Reports noted the P-51 Mustang's impressive range and high-altitude performance. They documented the P-38 Lightning's twin-engine speed and the P-47 Thunderbolt's rugged durability. Japanese planners recognized these aircraft as formidable opponents, but their analysis rested on a critical assumption that American fighters were operating at or near their maximum design performance. The Mustang's 437 mph top speed, the Lightning's 414 mph, the Thunderbolt's 433 mph. These figures were cataloged, studied, and integrated into tactical planning. What Japanese intelligence never detected was the Allied fuel chemistry program. No reconnaissance aircraft photographed the 17 refineries producing 130-grade fuel across America and Britain. No agent reported the purple-dyed barrels being loaded onto transport ships. No intercepted communication revealed that American and British chemists had moved beyond 130-grade into experimental 150-grade production. The assumption, logical, reasonable, and entirely wrong, was that Allied fighters were already performing at their peak, that the performance envelope was fixed, that the war would be fought with the capabilities both sides currently possessed. Japanese commanders planned accordingly. They developed tactics to exploit the Zero's superior maneuverability against the Mustang's speed. They positioned interceptor units to maximize the Oscar's climbing ability. They trained pilots to force engagements at altitudes and speeds where Japanese fighters retained advantages. They never anticipated that the Americans were about to rewrite the performance standards of aerial combat without changing a single aircraft design. The blind spot was absolute, and it would prove fatal. The story of how this advantage came to exist begins not with the war, but with the peacetime work of petroleum chemists who understood that octane rating measured how much an air-fuel mixture could be compressed before spontaneous detonation occurred. Higher compression ratios meant more power from each combustion cycle. More power meant faster aircraft and higher operational ceilings. The science was straightforward, but the engineering required to produce high-octane aviation fuel at industrial scale was extraordinarily complex and entirely dependent on petroleum resources Japan simply did not possess. Octane ratings, by definition, cannot exceed 100, because 100 octane means detonation resistance equivalent to pure iso-octane, the reference standard. Performance numbers measure how much better than pure iso-octane a fuel can perform. A fuel with a performance number of 150 means it can withstand 50% more compression than pure iso-octane before detonating. Achieving this required pushing beyond the natural limits of refined gasoline into the realm of chemical engineering. British fuel chemists at the Royal Aircraft Establishment began the critical work in 1942, testing numerous blends in search of the optimal combination. The foundation was tetraethyl lead, an anti-knock compound that had revolutionized automotive fuel in the 1920s. But tetraethyl lead alone could not reach performance number 150. The breakthrough came from blending aromatic hydrocarbons, primarily toluene and xylene, with the base gasoline in carefully calculated proportions. These compounds, derived from coal tar and petroleum cracking processes, dramatically increased detonation resistance. American researchers at Wright Field conducted parallel investigations, sharing data with their British counterparts through a collaboration that would have been impossible for Japan's isolated scientific community to replicate. By early 1943, both nations had produced experimental batches of what they designated as 150-grade fuel. The designation was somewhat misleading because it implied an octane rating of 150, which was chemically impossible. What it actually meant was a fuel with a performance number of 150 on the rich mixture scale, combined with 100 octane performance on the lean mixture scale. This fuel, dyed purple for easy identification and to prevent accidental use in non-compatible engines, underwent rigorous testing through 1943. Merlin engines running on 150-grade fuel could sustain manifold pressure readings of 75 inches of mercury, compared to 67 inches on 130-grade fuel. This translated directly into increased horsepower. A Packard Merlin, a 1657 generating 1,190 horsepower at standard military power on 130-grade fuel, could produce 1,720 horsepower on 150-grade fuel at war emergency power settings. The implications were profound. No airframe modifications were required, no engine redesigns, no new aircraft development programs. The P-51 Mustang sitting on the flight line today could become a fundamentally more capable weapon tomorrow simply by changing what flowed through its fuel lines. New fuel handling protocols were implemented. The tetraethyl lead content made 150-grade fuel toxic, requiring special storage containers and strict safety procedures. Ground crews received training on the purple-dyed fuel's handling requirements, but these were minor logistical challenges compared to the strategic advantage being created. Allied chemists had weaponized the periodic table. They had turned petroleum refineries into armories, producing a substance that could transform existing fighters into aircraft Japanese engineers had never planned to counter. Chemistry had become an instrument of war as decisive as any gun, bomb, or torpedo, and production was already scaling toward industrial volumes Japan could never hope to match. Flight testing at Wright Field confirmed that the performance gains were substantial across all flight regimes. Maximum speed increased by approximately 50 to 55 miles per hour at altitude, far more dramatic than the gains seen in European theaters. A P-51 Mustang that had reliably reached 437 mph on 130-grade fuel now pushed toward 490 mph on 150-grade fuel at 25,000 feet. The same aircraft, the same pilot, the same atmospheric conditions. The only variable was the purple liquid flowing from the fuel tanks into the Packard Merlin's combustion chambers. Climb rate improved by several hundred feet per minute. A Mustang running 130-grade fuel could climb at approximately 3,075 feet per minute at sea level. On 150-grade fuel, that figure jumped to nearly 4,000 feet per minute. The aircraft reached combat altitude faster, conserved more fuel during the climb, and arrived at operational height with energy reserves that translated directly into tactical flexibility. But the most dramatic transformation appeared in combat maneuvers. Acceleration during high-speed dives became ferocious. Zoom climbs, the vertical maneuver where a pilot converts speed into altitude, reached heights that left Japanese pilots struggling to track their targets. Energy retention in hard turns improved because the engine could sustain higher power settings without detonation risk. The Mustang had always been fast in level flight. Now it was fast everywhere, climbing, diving, turning, accelerating out of defensive brakes. The boost pressure increase from 67 inches of mercury to 75 inches of mercury represented more than numbers on a gauge. It represented the difference between an engine operating within conservative safety margins and an engine pushed to the edge of its structural limits, but held there safely by fuel chemistry that prevented catastrophic detonation. Pilots could firewall the throttle in combat emergencies. Watch the manifold pressure surge into ranges that would have destroyed the engine on lesser fuel, and trust that the Merlin would hold together. That confidence changed everything. For Japanese pilots, the implications were catastrophic. The Zero's maximum speed of 350 mph had always been adequate because Japanese doctrine emphasized forcing opponents into slow-speed turning engagements, where the Zero's maneuverability dominated. Against Mustangs running 130-grade fuel, this tactic remained viable. A skilled Zero pilot could evade, disengage at low altitude, or force the fight into slow-speed regimes where American speed advantages diminished. Against Mustangs running 150-grade fuel, those options vanished. A P-51 pilot could dive from altitude at speeds exceeding 500 mph, close on a Zero in seconds, fire a burst, then zoom climb back to altitude before the Japanese pilot could even react. If the Zero attempted to flee, the Mustang simply ran it down. If the Zero turned to fight, the Mustang could refuse the engagement, climbing away at rates the lighter Japanese fighter couldn't match while maintaining enough speed to return and attack at will. Japanese fighters became prey. They could not retreat safely because American fighters were faster. They could not engage effectively because American fighters dictated the terms of combat. They could not disengage because American fighters could pursue indefinitely. Every tactical advantage Japanese aviation had built into the Zero, the Oscar, even the newer George, maneuverability, climb rate at low altitude, tight turning radius, became irrelevant against an opponent who simply refused to fight on those terms. The Americans had evolved beyond the dogfight. They had turned aerial combat into a hunt, and chemistry had given them speed that made them untouchable. The first combat reports arrived in late summer 1944, filtering back from fighter units stationed across the Mariana Islands and the Philippines. The language was consistent: confusion, disbelief, and something approaching fear. Zero pilots described American Mustangs performing maneuvers that defied their intelligence briefs. Experienced flight leaders filed after-action reports claiming P-51s were accelerating unnaturally during high-altitude pursuits. Squadron commanders initially dismissed these accounts as combat stress or pilot error. Then the reports multiplied. Lieutenant Saburo Sakai, one of Japan's most skilled and respected fighter aces, encountered a flight of Mustangs over Iwo Jima in August 1944. Sakai had survived years of combat through situational awareness and an intimate understanding of his opponent's capabilities. He knew the P-51's performance envelope. He had fought Mustangs before. This time was different. He initiated a climbing turn, a defensive maneuver that had saved his life dozens of times, expecting the American fighter to lose energy and break off. The Mustang stayed with him. Then it accelerated past him. Sakai's Zero, already at maximum power, watched the American fighter pull away vertically, climbing at an angle that shouldn't have been possible. His report to command was blunt. The enemy aircraft performance has changed. Previous engagement parameters no longer apply. Over the Philippines in October 1944, Japanese interceptor units scrambled to engage American B-29 formations, targeting Luzon. The doctrine was straightforward: climb to altitude, position ahead of the bomber stream, then dive through the formation in slashing attacks before the escort fighters could react. Mustang escorts were factored into the planning. Their speed was known. Their range was respected. But range and speed calculations were based on outdated performance data. The reality shattered Japanese attack plans. Mustangs at 30,000 feet saw the Japanese fighters climbing and simply dove to meet them. What followed wasn't a dogfight. It was a slaughter. American pilots pushed their throttles forward and felt the Merlin engines howl as boost pressure climbed to 75 inches. The Mustangs accelerated through 450 mph, then 460, slashing through Japanese formations before the Zero and Oscar pilots could even track them. Gun camera footage captured the confusion. Japanese fighters braking in all directions. Pilots attempting evasive maneuvers that had worked against previous American attacks, only to find Mustangs staying with them through every turn, every dive, every desperate attempt to disengage. Survivors described the same phenomenon. American fighters that refused to turn fight but didn't need to. They simply outclimbed, outdove, out-accelerated everything Japan could field. Dogfighting as Japanese pilots understood it. The swirling close-range knife fights where agility and pilot skill determined outcomes had been replaced by something colder and more mechanical. The Americans attacked in vertical yo-yos, boom and zoom passes executed at speeds that left Japanese pilots reacting to where the Mustangs had been, not where they were. One Zero pilot, struggling to process what he'd witnessed, radioed his flight leader, "They are not fighting us. They are hunting us." Word spread through frontline units stationed across the Pacific. Veteran pilots traded accounts in hushed conversations. The Americans had changed something fundamental. The Mustang wasn't just fast anymore. It was impossibly fast. And no one in Japanese command seemed to know why. The reports reached Imperial General Headquarters in Tokyo through official channels. Typed combat summaries, unit after-action debriefs, intelligence assessments from field commanders. The language varied, but the message was consistent. American P-51 Mustangs were demonstrating performance characteristics that exceeded all known specifications. Maximum speed estimates were revised upward. Climb rate figures no longer matched pre-war intelligence. Acceleration during combat maneuvers defied engineering expectations. Senior staff officers reviewed the data with skepticism bordering on dismissal. One admiral scrawled across a particularly detailed report: "Pilot exaggeration under combat stress. Disregard." The alternative, that American fighters had somehow achieved a fundamental performance breakthrough, was too operationally devastating to accept without incontrovertible proof. Japanese aeronautical engineers were tasked with explaining the discrepancy. They studied captured intelligence photographs of P-51s, searching for modified engine cowlings, redesigned exhaust stacks, or enlarged supercharger intakes that might account for increased power output. They found nothing. The Mustangs looked identical to earlier variants. Engineers at Mitsubishi Heavy Industries ran calculations on the Packard Merlin engine, exploring theoretical maximum performance if compression ratios were increased or boost pressure pushed beyond safe limits. Their conclusion? Such modifications would increase power briefly, then destroy the engine through detonation. American pilots couldn't be flying aircraft on the verge of mechanical failure. Their operational sortie rates proved the engines were reliable. The answer eluded them because they were looking for airframe or engine modifications. They never considered fuel. Meanwhile, the Imperial Navy Air Service faced a separate crisis that compounded the tactical situation. Fuel supplies were collapsing. American submarines had systematically destroyed the tanker fleet that transported crude oil from the Dutch East Indies to Japanese refineries. By late 1944, fuel reaching frontline units was often cut with pine root oil or other substitutes that reduced octane ratings even further. Pilots reported rough-running engines, decreased power output, and increased maintenance requirements. Aircraft that should have been capable of 350 mph were struggling to reach 320 yaw. The performance gap between Japanese and American fighters, already significant, widened with every passing week. Flight training programs shortened as fuel allocations dwindled. New pilots arrived at operational units with fewer flight hours, less gunnery practice, and inadequate experience in high-altitude tactics. Veteran pilots, those who had survived the grinding attrition of 1943 and 1944, looked at their inexperienced wingmen and knew the odds. Against Mustangs running at full performance, even skilled pilots struggled. Against Mustangs that somehow outperformed their own specifications, survival became a matter of luck. Morale reports from forward bases reflected the shift. Unit commanders noted declining confidence among pilots facing escort missions. Some pilots openly questioned whether interception missions against B-29 formations, escorted by Mustangs, were tactically viable or simply suicide assignments. The psychological impact of fighting an enemy who could dictate every engagement, who could attack or withdraw at will, eroded combat effectiveness as surely as fuel shortages and pilot attrition. In Tokyo, staff officers continued to debate the intelligence reports. Some argued the Americans had introduced a new Mustang variant not yet identified. Others suggested Allied propaganda was inflating combat performance to demoralize Japanese forces. A few cautious voices noted that, if the reports were accurate, Japan faced a tactical problem with no immediate solution. But none of them understood they were fighting chemistry. And by the time Japanese intelligence finally identified 150 grade fuel as the source of American performance gains, it was far too late to matter. The disparity between American and Japanese fuel production was not a matter of technical knowledge or engineering capability. It was a matter of geological reality and industrial infrastructure, factors that no amount of tactical brilliance or pilot courage could overcome. Japan's home islands contained virtually no petroleum reserves. Every gallon of aviation gasoline required crude oil imported from conquered territories in the Dutch East Indies, transported across thousands of miles of ocean, then refined in facilities that were primitive compared to American installations. At peak production in 1942, Japanese refineries produced approximately 600,000 barrels of aviation gasoline annually. This volume was sufficient for defensive operations and limited offensive campaigns, but it left no margin for expansion, no reserves for increased sortie rates, and no capacity to develop advanced fuel formulations. By contrast, American refineries in 1943 were producing aviation gasoline at a rate exceeding 20 million barrels annually. 17 facilities across the United States operated catalytic cracking units using the Houdry process, technology that allowed refiners to break down heavy crude oil molecules into high-octane gasoline components with unprecedented efficiency. These refineries could produce 100-octane fuel as a baseline product, then further enhance it to 130 grade or 150 grade through chemical additives and aromatic compound blending. The scale was incomprehensible to Japanese planners. A single American refinery complex in Texas could produce more high-octane aviation fuel in 1 month than Japan's entire refining infrastructure produced in 6 months. And American production was still accelerating, driven by military demand and supported by virtually unlimited crude oil supplies from domestic fields in Texas, Oklahoma, and California. Japan's fuel supply chain began collapsing in 1943 as American submarine warfare intensified. Tankers carrying crude oil from Palembang and Balikpapan to Japanese refineries became priority targets. By 1944, submarine captains were filing reports of multiple tanker kills per patrol. Each sinking represented not just lost crude oil, but lost refining capacity, because the tankers themselves could not be replaced at a rate sufficient to maintain supply flow. Those supplies that did reach Japan faced another obstacle: strategic bombing. American B-29s began targeting Japanese refineries and fuel storage facilities in late 1944. Precision attacks on catalytic cracking units and distillation towers caused damage that took months to repair, if repair was even possible given the scarcity of replacement parts and skilled technicians. Fuel quality deteriorated as refineries operated at reduced capacity, cutting corners on distillation processes to maintain volume at the expense of octane rating. By early 1945, frontline Japanese units were operating on fuel that averaged 85 octane or lower. Some units reported fuel so contaminated with impurities that engine failures during takeoff became routine. Pilots learned to nurse their engines, avoiding full throttle settings that might cause detonation. Aircraft performance suffered accordingly. Meanwhile, American production of 150-grade fuel reached industrial scale. Millions of gallons flowed from refineries to port facilities, loaded onto transport ships, and distributed across the Pacific theater. Fighter groups in the Marianas, Iwo Jima, and Okinawa had access to fuel supplies that dwarfed Japan's total national production. Ground crews handled the purple-dyed fuel with practiced efficiency. Pilots flew combat missions, knowing their aircraft would perform at maximum capability. The resource divide had become absolute. Japan was fighting an industrial power that could produce advanced aviation fuel faster than Japan could produce basic gasoline. No tactical innovation, no operational strategy, no pilot training program could bridge that gap. The war had become a contest of refineries and chemical plants, a contest Japan had lost before the first Mustang ever climbed to altitude on 150-grade fuel. By early 1945, the transformation was complete. American P-51 Mustang units operated across the Pacific with a freedom of action that would have been unthinkable 2 years earlier. Fighter groups based in the Marianas flew escort missions to Tokyo, a round-trip distance exceeding 3,000 miles, and still had fuel reserves for extended combat over the target area. The Mustang's legendary range, combined with 150-grade fuel's performance advantages, created an aircraft that could appear anywhere, at any time, with speed and endurance Japanese defenders could not match. Japanese interception attempts became exercises in futility. Radar stations detected incoming American formations and scrambled available fighters, but the tactical calculus had shifted beyond recognition. Japanese pilots climbed to intercept altitude, knowing they would face aircraft 100 mph faster. With superior climb rates, better acceleration, and operational endurance that allowed American pilots to circle overhead while Japanese fighters burned through their limited fuel reserves. Combat reports reflected a grim arithmetic. Japanese fighters might achieve advantageous position briefly, but Mustangs could simply accelerate away, reposition, and attack again at will. Naval convoy protection collapsed entirely. Japanese cargo vessels attempting to move supplies between home islands and remaining occupied territories required air cover to survive American fighter sweeps. But providing that cover meant positioning fighters at vulnerable altitudes where P-51s hunted with systematic efficiency. Ship captains reported watching their escorts shot down within minutes of engaging American fighters, leaving convoys defenseless against follow-up strafing attacks. Losses mounted until daylight convoy operations became essentially impossible. American pilots, meanwhile, fought with a confidence that bordered on aggression. They had learned through experience that their aircraft held decisive advantages in every performance category. Engagement decisions became simple. If a target appeared, attack. If Japanese fighters responded, press the attack. The Mustang's speed provided an escape option if combat turned unfavorable, but increasingly, combat didn't turn unfavorable. Japanese pilots flying underpowered, fuel-starved fighters against Mustangs running 150 grade fuel were outmatched before the first shots were fired. Gun camera footage from this period captures the imbalance. American pilots pursue Japanese fighters through extended chases, maintaining position through climbs, dives, and turns that should have allowed the lighter Japanese aircraft to escape. The Mustangs stay with them, patient and inexorable, until firing solutions develop. The footage is clinical, almost methodical, evidence of combat that had ceased to be a contest and become simply execution. Japanese air power, which had dominated Pacific skies in 1941 and 1942, fragmented under the sustained pressure. Pilot losses exceeded replacement training rates. Fuel shortages grounded aircraft that remained mechanically operational. Airfields came under regular attack from fighters that could loiter overhead for extended periods, destroying aircraft on the ground when they couldn't find targets in the air. By mid-1945, organized Japanese air resistance had effectively ceased in most operational areas. Remaining fighters conserved fuel for final defensive operations, hoarded by commanders who understood their forces could no longer contest American air superiority. The collapse was total. American fighters roamed Japanese airspace as if they owned it, because functionally they did. The industrial imbalance that began with petroleum geology and refinery capacity had cascaded through fuel chemistry, aircraft performance, and tactical capability until it produced absolute aerial dominance. Japan's pilots, many of them brave and skilled, fought an enemy they could not catch, could not escape, and could not defeat. Chemistry had decided the outcome. The rest was simply enduring the inevitable. Japanese intelligence services spent years tracking American aircraft development programs. They documented every new fighter variant that entered service, cataloged performance specifications from captured manuals and combat observations, and maintained detailed assessments of Allied aviation capabilities. They anticipated improved versions of existing aircraft. They expected entirely new designs might emerge from American factories. They prepared tactical responses for faster fighters, better armed interceptors, and aircraft with extended operational ranges. They never anticipated that the Americans would chemically transform the fighters they already possessed. The story of 150 grade fuel reveals a fundamental truth about industrial warfare that Japanese planners understood intellectually but failed to account for strategically. Modern combat is not decided solely by the weapons fielded on the battlefield, but by the industrial and scientific infrastructure that produces those weapons. Japan built exceptional aircraft with the resources available. The Zero remains one of history's most iconic fighters. But exceptional design cannot overcome resource scarcity, industrial capacity limitations, and technological gaps in supporting infrastructure. The P-51 Mustang running on 150 grade fuel represented the convergence of multiple American advantages. Petroleum geology that provided virtually unlimited crude oil. Refining technology that could transform that crude into advanced aviation gasoline. Chemical engineering that pushed fuel performance beyond natural octane limits, and industrial capacity to produce millions of gallons at volumes Japan could not approach. The aircraft itself, designed by North American Aviation, powered by a Rolls-Royce engine built under license by Packard, was merely the delivery system for chemistry that turned good fighters into dominant ones. The performance transformation was absolute. A Mustang that had reached 437 mph now approached 490 mph. Climb rates increased by hundreds of feet per minute. Acceleration during combat maneuvers became unmatched in the Pacific theater. And critically, these gains required no airframe modifications, no engine redesigns, no lengthy development programs. The transformation occurred as quickly as fuel could be distributed to forward bases and loaded into aircraft tanks. Within months of 150-grade fuel's operational introduction, the performance gap between American and Japanese fighters had widened from significant to insurmountable. The Pacific Air War, viewed through this lens, becomes a story not of aerial tactics or pilot skill, though both mattered, but of chemistry, refineries, and strategic resource allocation. It becomes a narrative about industrial capacity and scientific advancement as instruments of military power. Japanese pilots fought bravely with the tools their nation could provide. American pilots fought with tools enhanced by chemical breakthroughs their opponents could neither replicate nor counter. When the war ended in August 1945, analyses of Japanese defeat emphasized many factors: numerical disadvantages, strategic overextension, failed defensive doctrine, and the atomic weapons that finally compelled surrender. But in the skies above Japan, where American fighters roamed with impunity during the war's final months, the outcome had been decided by something more prosaic than brilliant strategy or revolutionary technology. It had been decided by purple-dyed aviation gasoline flowing from American refineries at rates Japan's petroleum-starved empire could never match. The Americans hadn't just outfought Japan. They had outproduced them, out-refined them, and ultimately out-chemisted them. And in that disparity lay the entire story of how the P-51 Mustang became untouchable. Not through new designs, but through fuel that turned good aircraft into demons the enemy never expected and could never escape.